So far I've looked at the general case where I did not know the details of the temperature distribution along the top side or edge. I now want to look at a specific case where the top edge is at a different temperature but a uniform temperature to the three other edges. So these are the three other edges at temperature T0, and the top surface or edge is at a temperature T1, which is higher than T0. As before, I'm going to subtract out the uniform temperature T0, so the new top surface or top edge temperature will be T2 equals T1 minus T0. Putting that into this integral, which came out of the general solution case, T2 is a constant, so I can take it outside the integral, so I've simply got the integral 0 to L sine of n pi x over L with respect integrated with respect to dx. That simply integrates to minus L over n pi cos of n pi x over L to be evaluated between 0 and L. If x equals 0, that integral gives us minus L over n pi cos of 0, which of course is 1, gives us an overall result of minus L over n pi. If x equals L, then if n is even, I again get minus L over n pi, whereas if n is odd, I get plus L over n pi. Basically because if n is even, I have cos of 2 pi, 4 pi, etc., and the value of that is 1, where if n is odd, I have cos of pi or 3 pi, 5 pi, etc., and in that case the value of it is minus 1. Putting that together means that if n is even, the overall integral gives us a value of 0, where if n is odd, we get a non-zero value of 2L over n pi. Thus, for our overall temperature distribution, the Cn terms are non-zero if n is odd, and specifically in this case they are 4 times T2 divided by n pi cos h of n pi h over L, whereas if n is even, Cn is 0. Now, it's a little inconvenient to write down equations where you say n is odd or even, so one way of ensuring that we don't have to do that is to define n in terms of some other number m. So in the forms that we say n equals 2m plus 1, then if m is 0, we have 2 times 0 plus 1, it gives us n as 1. If m equals 1, we have 2 times 1 plus 1 gives us n equals 3. M equals 2 gives us 2 times 2 plus 1, giving us n equals 5, etc. Thus we can write our overall temperature distribution, also adding it back in T0, as being T equals T0 plus 4T2 over pi, the sum now of over m, where m goes from 0 to infinity and replaces all our original m terms. So we now have 1 divided by 2m plus 1 sine of 2m plus 1 pi x over L times sinh of 2m plus 1 pi y over L times cos h of 2m plus 1 pi h over L. And that is actually our formal temperature distribution for the case where the top edge has an elevated uniform temperature, which is different from the uniform temperatures along the other edges. Now, just to see if this works, this shows us what the temperature distribution would look like if we only took the first term of that summation. Clearly that's not a very good approximation to a uniform temperature along the top edge. If we add first two terms, things look a little better, and if we then go to 3 terms, they look better still. 10 terms further improved, although we're now seeing some apparent bumps here which are due to the fact that this mesh I've taken is not particularly fine. 20 terms and then 100 terms, things further improve, strictly again because the mesh I've taken isn't exceptionally fine. You never actually get a perfect match at these corners. There is always an overshoot here, which is known as the Gibbs phenomenon, and this is specifically to do with the fact that we effectively have a temperature discontinuity at the corner where it suddenly changes from being T0 to T1. Now you might think you could differentiate the temperature distribution to obtain the heat fluxes, and I've formally done that here. So this is what you would get by using Fourier's law and differentiating, and it looks like these are solutions. However, in this particular case, these series do not converge. So therefore the equations on the last side do not give the heat fluxes. If you could look at the QX case, so nominally the flux in the x direction, you can see it alternates becoming more positive and then more negative and ever larger, whereas the QY case, it just oscillates between two values. Essentially this is because when you differentiate these terms, in this particular case, there is no longer any division by 1 over 2m plus 1. If we go back to the temperature terms, you'll see we've got 1 over 2m plus 1. So as we go to larger values of m, this term will always get smaller, whereas these terms don't show that sort of behaviour. We've now lost that division term here, and thus all we see is the oscillatory behaviour of these functions. Thus in this particular case we cannot obtain the fluxes from the temperatures. That's not always the case with Fourier series, but it is a specific problem with this particular Fourier series. One which doesn't give the same problem, and which I would like you to have a go at trying to fit, is a triangular variation in temperature along one side. So I've given some details here. Please have a go at this for next time. So to summarise this lecture, what I've looked at are two-dimensional steady-state cases with no internal heat generation, and particularly I've done this in Cartesians and dealt with Fourier series solutions. And then I looked firstly at the general case, then at the specific case for a uniform elevated temperature along one side, and on that particular case you can't differentiate the temperature solution to obtain the heat fluxes. And I've left you with the problem of a triangular temperature distribution along the top surface, which you should have a go at trying for next time. Thank you.